Thanks, Andy. So this is a talk about stateful processes in probabilistic programming, which I think Sam talked a lot about in his talk as well earlier. But it's really a talk about game semantics, so I've changed my title from the program to reflect that because I was a bit worried about misleading people. So the plan of the talk is to just go through 3 very well-known, I think, examples of when state is useful to implement interesting probabilistic models. And then I'll move on to showing how the model works, how game semantics works in general, and then with probability, and how it can help us to reason about state in this context. My first example is I think the obvious one. It's just an urn scheme where the state here is what's in the urn, so maybe the number of balls of each colors, and the reason state is useful here is because you can very easily implement the procedure for drawing and for sampling and replacing the balls in the urn. So this is, I think Sam had this as well. It's just the implementation of a poly urn where the state just has two integers corresponding to balls of each color, and then you sample one, and you sample a random ball and just add one more of the colors that you've picked. So this is an interesting one, but of course, urn schemes are much more general in probability theory. They don't necessarily have to be exchangeable, and generally a stateful language is useful to implement this kind of thing. Okay, sorry. So my second example is a Gaussian process, a kind of random function, which is also very useful and also very nice in probabilistic programming, because you can implement it very nicely in a language with state. And here I'm using the same kind of abstract type ideas that Sam had, where the process corresponds to a mean and covariance functions. So these are just the standard parameters for a Gaussian process. But of course, as you sample more elements from a Gaussian process, so you sample these points from the random function, you know more about the process, and it's helpful to keep track of all the samples you've done so far so that you can adapt the distribution of the further samples. So this is, you need to do this, otherwise the implementation isn't going to be correct. So this is another example which I'll come back to in the game semantics. And my third example is a bit different. It's a well-known example in the theory of nonparametric statistics. It's called the Indian buffet process, and it's a way to generate a distribution on infinite matrices with Boolean coefficients. So this is useful for what's called feature modeling, where we don't know how many possible features the objects that we're looking at can have. So I'm not talking really about the application. This is just the way to generate the matrices. So the idea is there's an Indian restaurant, or there's a restaurant with infinitely many possible dishes to take, and customers are coming in one by one. And for each customer, so here, this is one customer, they're going to sample a certain number of dishes, a finite number of dishes. And when the second customer comes in, they're going to sample dishes from the ones that have previously been sampled, and then a few more possibly. So the process goes on in this way, and so we're generating a matrix with Boolean coefficients in this way. And this happens to be exchangeable, and so it has very nice theory. The reason I'm including it as an example here is I think it's quite an interesting one from the perspective of the data flow property, and I'd like to understand more I'd like to understand more about this process, because it's exchangeable, even though it seems like an implementation without state would be very difficult to obtain, possibly because of the infinities in the number of dishes that can arise. I'm not really sure. But in any case, a sample from this process just gives you, for every customer, a list of Booleans corresponding to the dishes sampled by this one customer, or the features that this one object will have. And of course, the process, the key point here is that as a customer is coming in, the dishes that they're sampling they're sampling dishes based on how popular certain dishes have been. So we need to keep track of not only the list of dishes that have been sampled so far, but also how many people have come into the restaurant so far and how popular each dish has been. So there might be some parameters to the process, normally a real number, but also we need to keep track of how many samples have come through so far, and also the list of dishes. So I think this has got an interesting model as well for stateful probabilistic programming. Okay, let me move on to the main topic of the talk, which is game semantics. So I'll start with game semantics in general, and then I'll move on to the more recent work on randomized game semantics. Okay, game semantics is a kind of denotational semantics, so we're interested in a mathematical representation of programs. And the basic idea is that each program is represented a bit like a tree, where the tree represents the interaction between the program and maybe some agent interacting with it. So we call that the environment. And so this kind of perspective has two interesting consequences, I think. The first one is that functions or higher order programs are represented just as a first order interaction, because that's the way you interact with a higher order program or with a function. You're just supplying it with first order arguments or receiving first order values. So it's just going to be, we don't have to ever explicitly represent functions or higher order functions. And the second consequence of this kind of perspective is that the state and the representation of state is completely implicit. So we never have we never have to think about a set of possible states or this kind of thing. A stateful program or a stateful object is completely characterized by the way that you interact with it. So here's a very basic example of a function which always returns false. So it's like a thunk. It ignores its argument and just returns false. And here's the representation of this kind of function in game semantics. So it's a kind of tree. The blue nodes here correspond to the action of the program itself, and the red nodes correspond to what the environment is doing. So here the lambda is just because this is a function, and then of course what the environment can do here is just call the program any number of times. So this is just a finite portion of an infinite tree where you can see where this is going. Every time the environment calls the program returns false. Okay, and so some comments about this. There's two players in this game, the program and the environment. I've said this. And I think an interesting aspect of this representation is that the repeated calls are represented explicitly. This isn't always true in semantics. So this is a special kind of semantic theory where the linear structure is explicitly represented. So that's why I'm using the kind of linear logic notation here with a linear arrow and a linear duplication operator. So this just says an infinite, countably infinite duplication of nodes. And this explicit duplication leads to some interesting symmetries in the program, which I'll get back to in a minute. And another comment is that partiality. So partiality is built into the model. So here, of course, this function is a total function, but I could have had a function that just fails every time or diverges. And then I could, within the same model, I could just say the program does nothing every time it gets called, and we get a similar kind of representation. Okay. So let me move on to randomness. So if we're in a probabilistic program, we'd like the semantics to reflect the random behavior. So here, often people in game semantics or in semantics talk about distributions and probability coefficients put on nodes. Here I'm taking a slightly different view where we're looking at random variables rather than probability distributions. This is part of what's helpful to reason about state. So we have an ambient probability space, and what the program does is of course random. So this is an example of just a normal distribution. So again, thunked. So it's just a function which gets called and returns a real number every time it gets called. And these xi here that I have, so there's infinitely many of them, they're just IID because every time you call the function, a new sample is produced. So they're just IID with respect to a sample from the standard normal. So here's a different program where the sample is done outside of the lambda, as it were. So you sample a real number, and then create a function which returns that real number every time it gets called. So this has the same type, so the representation looks very similar, except that this time the random variables are all equal. They're completely correlated. They're exactly the same random variable. So if you fix the random seed, you'll just get the same value every time, which is exactly how this program behaves. Okay, I hope this is clear. Here's a more interesting example where now it's a function that has an argument, so it's an actual random function. In fact, this is what we're going to use to model Gaussian processes or things of the same type. So here, it's not just a thunk. The environment, so the red nodes, also supply a value to the program. So every time there's an input real number, you get a real number out. And this time, the value of these random variable xi is parameterized by not only the random seed, but also the value of the environment. So you get countably many of these functions here. And of course, they have to be measurable for it to work. So I think this is a very nice representation of a Gaussian process, which doesn't involve a very complicated measure theory or anything. You just have countably many of these functions, which in fact are all the same and correspond to if f is the random variable corresponding to this Gaussian process, f of t is a random variable for every t in R, and that just determines what these variables are. Okay, so just two comments. This is what I've said, that the behavior of the program is parameterized by everything that the environment has done so far. And the second comment is that we need to somehow enforce symmetry. So here, I'm not saying it. So at the moment, I'm not saying anything about how these are connected, but we'll see that there needs to be some symmetry. So I'll get to that in a minute. Now let me present the model a little bit more abstractly. So randomness here just means that the control flow is non-deterministic. So we need a representation not only for the kind of temporal history of the program, but also the possible branching that you can run into. So formally, what we do is we use event structures. It's not the only way to present this kind of game semantics model, but I think it's a convenient way because it's an old model for concurrency, which allows you to talk about both causality and causal order, and also non-determinism. So an event structure is a graph like this. It's really a partial order, so the events causally depend on each other. And then there's a structure for non-determinism so that's an additional relation on events which says which two events are incompatible. So here this might be this might be a program which on input R on some real number input can have two possible behaviors. So here, in order to talk about stochastic game semantics, we need to add even more structure and say that every event, so every blue event, every program event is now a parameterized random variable. But of course, because partiality has to be built into this whole framework, it's a partial random variable which will have some value, which either will have some value or will be undefined. And we need to say when a strategy makes sense in this context. You can't just put any kind of functions here. So first, let me say, if we have a strategy, so an event structure with this kind of structure, if I fix a random seed and I fix a value for every possible behavior of the environment, then I can define the sub-strategy or the substructure which corresponds to this random seed, just by looking at when these random variables are defined. And then I say that a strategy is a randomized strategy, so it's a strategy that makes sense from a probabilistic perspective, if for every possible random seed and action of the environment, this substructure is a well-defined deterministic strategy. So then the behavior of the program is well-defined and deterministic, which it should be once I fix the random seed. Okay, let me go back to an example which is actually completely deterministic, and I'll come back to this in a second. So this is the example of a memoization strategy. So memoization, stochastic memoization, is very useful in probabilistic programming. It allows you to build interesting infinite dimensional models. Here, this is a very boring kind of memoization where we just have a function from like a thunk, which gives you a Boolean. So this is not very interesting, but in fact, in game semantics, all that really matters is the dynamics. That's what's hard to represent. So that's what I'm using here as an example. But in fact, in game semantics, it's not hard to move to measurable, to add measurable structure, as we've seen. And so this is the same exact thing happens for memoization, a more interesting kind of memoization. So what happens in this strategy? So here there's an input function and an output function. So when the environment supplies an input function, the program just returns a new function. And this new function, if you call it, it'll call the original function and just copy whatever the answer is. But if you call it again, it will just return what the first answer was. Okay, but of course, this depends on what the first value, what the initial answer was. So there's an additional causal link here. So you can see how this causality structure is really used crucially here. And of course, the first answer didn't have to be true in this case. It could have been false. And so, then there would have been a whole other part of the strategy, which I don't have the space to draw. Okay, this is a deterministic strategy because everything that the program does is completely determined by the behavior of the environment. But there is one slightly technical point, which I think is still interesting to mention, is that we have to assume the environment is sequential. So in this case, what I've drawn on the slide here, it makes sense. The execution of this program makes sense as long as these calls are coming in sequentially. But event structures often are used to talk about concurrency, and in fact, we have to talk about when these two calls to the memoized function are occurring at the same time. And here, what happens is that there's a race, because of course, if you're saying only one of those calls is going to call the initial input function, and the other one's just going to copy it, well, one of them has to win the race. So there is going to be some kind of non-determinism. So you have to be a bit careful when you talk about being a deterministic strategy. So this is for a sequential environment. Okay, now I'll move on to this idea of symmetry, which I've talked about. It comes from having this duplication of function calls and this underlying linear logic structure. And we have to talk about uniformity, which is really enforcing the symmetry to make sure that the strategy is well behaved. So a strategy is a picture a bit like this. This slide is going to be a bit abstract, but I'm trying to make it clear. So in fact, the strategy it lives over a game. So this might be the strategy sigma, but there's an underlying game which has just the possible values that a program of this type can play. But it won't have all of the constraints or all of the order. It'll just have some possible values. And there's a map relating them this way. So this is the obvious map. And then there's two kinds of symmetries because we're talking about behavior of the program and the behavior of the program's environment. So now we have these two kinds of moves. And what it means to be uniform is that the program reacts to a possible reshuffling of the environment environment moves. So there's two kinds of symmetries here, and for every possible reshuffling of the environment, there is going to be the strategy can adapt to this, and there's going to be a symmetry of the strategy as well. So what this is saying is, as soon as the environment decides to call the function in a different order, the program behaves in exactly the same way, up to equality and distribution, of course, in this case. Okay, this is based on some older work on game semantics, which I've had to adapt to this setting. But I think it's interesting in the context of nonparametrics as well. So let me show an example here. If I go back to my Gaussian process example, or any random function really in this case, if I represent this function as a strategy which is uniform, it means that my sequence of randomized kernels here has to be exchangeable in an appropriate sense. So, well, in the standard sense, but kernels rather than random variables. But I think it's interesting to look at what uniformity means a bit more generally, because I've not said anything about restricting state so that everything is exchangeable. In a language with state, you can have any kind of behavior. And for instance, you could have a counter which just returns the number of times it's been called. And so it's just going to output 1, 2, 3, 4, and so on. And of course, that's not exchangeable. So this is well known. But game semantics is a very general framework. It allows you to talk about this. And so here, so this would be a very small portion of the strategy representing a counter, where if you call the strategy one time, you might get a 0. If you call it a second time, you might get a 1, because you can't get 0 twice, and so on. And uniformity does apply here, so we have to be very careful about about formalizing this kind of strategy. So in some sense, uniformity and symmetries in game semantics go a bit beyond what the kind of symmetries we have in statistics. Okay, this is the general story. State is useful. I think the point's been made before about it's useful to implement lots of interesting processes in probability, and it seems to be essential even in some cases, or at least very natural. And game semantics is a good way to reason about state, and I probably should have had more references here. Game semantics is well known to be a model for state. I think this is the first time that there's really a model for state probability and concurrency in this way. And it's interesting in the context of studying symmetries in probabilistic programs as well. And I'm interested in whether there's the underlying linear logic structure is really what's useful here. And I wonder if some other, maybe slightly simpler models of linear logic can help reason about this kind of idea, especially when it comes to exchangeability, because the generality of game semantics, as I've said, goes beyond the simple idea of exchangeability. And so possibly some more extensional models of linear logic can be a bit more informative in this case. Yeah, I'm happy to answer questions.
Hugo, thanks ever so much for a fantastic talk.
Yeah, thanks.
There are already a couple of questions. Oh, I can see that you can see them. And I just say, folks, if you've got more questions, please drop them in the Q&A or raise your hand and you can ask them directly.
Do you want me to answer them, or?
Please go ahead. Yeah.
Okay, so I'll just choose. I don't know if you've selected one, or if I should. Oh, okay, sorry, I can see that now. Are there any limitations on omega, the space of random Cs? Yeah, so that depends on how. Generally, what you need is the sample spaces. You can split it into countably many parts, which is generally what you need for any sample space. I think that's enough for the Gaussian process example, depending on how you implement it. If you just want to have a Gaussian process primitive in your language, then you need whatever is needed to formalize a Gaussian process in probability theory, which I think often is a bit more than like the reals or something. I don't know if that. Okay, I guess Alex is not going to respond. Okay.
Alex, would you like to respond? You can raise your hand and we can invite you to the stage. We do have a little bit of time. It's 9 minutes till the next talk.
Oh yeah, I was quicker than I expected.
Oh, here's Alex. Great.
Oops. Hey.
Hi, Alex. Thanks for the question.
Oh, sorry. I mean, I guess I was thinking about when you were talking about these things as random variables, how sometimes stochastic processes we don't formalize as like a single random variable, right? Like with a sample space and then a measurable function to read out the value. I was wondering here, you mentioned that it was like maybe more than R that you would need to formalize a Gaussian process.
Yeah. No, that's I think
Yeah.
So it's what I said. I think if you're just talking about implementing state, what you really need is for the structure of the model is to be able to duplicate it countably many times. But I think if you want a Gaussian process primitive, then you need the. I think in order to have the uncountably many random variables, the sample space needs to be quite big. Yeah.
Thanks.
Do you have a follow-up question, Alex?
Well, is it a different sample space for every primitive or every function in your language, or like?
No, it shouldn't. No, it's not. No.
I see.
Okay, thanks, Alex. We also had a question from Cameron. I'll just read it out, but it's in the Q&A. He said, and Cameron, you might want to join the conversation here also. He says, just to comment your point about the difficulty of finding stateless representations of the Indian buffet process. He says that Dan Roy had described some of the issues retruncation and slice sampling in a talk he had given that's on the web. Cameron, do you want to add anything to that?
Oh, yeah, I was just going to mention that, like some of us have started to think about, I think, some of the issues that were implicit in what you were saying about stateless representations for the IBP being sort of trickier in some ways than, say, for CRP or other nonparametric settings. And there's an issue that Dan had identified a while ago. If you care about like carrying out the transformation computably, aside from sort of the shape of the resulting object, that there's a kind of continuity obstruction because you can have closely related inputs that give rise to different outputs because you essentially can't tell if two sticks are very close versus being a single large stick, right? Like there's no amount of information that will actually distinguish those. So anyhow, there's some interesting obstructions in that case that don't happen in some other instances of exchangeability.
Okay, that sounds really interesting. Yeah, I think it's beyond what. My understanding was just that you needed to truncate. So you could do a kind of stick breaking, but you eventually had to. You couldn't get the full stick because you needed to look at every bit of stick in order to sample for any given customer, which isn't possible. But it sounds like, what you said.
Well, I mean, like the way in which truncation is used in practice, like there's basically this is pointing to maybe some reasons that that's not accidental, that people truncate in practice or implicitly truncate with slice sampling, and that this may be because of a deeper obstruction.
Yeah, I'm really interested. Yeah, I'll have a look at the reference. Thanks very much. No, I didn't have anything more to say than I tried to implement it and I couldn't. So.
Oh yeah, thanks for the talk.
Thanks.
Hugo, I've got a pretty broad question. Sure. So what do you think of the implications for inference? Given that this is a workshop on languages for inference, maybe we should. It's a general question.
Yeah, so I talked a bit in previous work I've done on how the kind of representation that game semantics gives you looks a bit like the graphical model representation that people, I think, use in practice to optimize Monte Carlo inference or this kind of thing. And so I suppose this is a general comment by game semantics for the act. I'm not sure how much of this previous work would apply to the more general game semantics I've talked about today for state, but I suppose there is a hope. I don't know. It would be nice if those representations could somehow be implemented and would maybe give an inference representation for probabilistic programs that you can actually use. I don't know if maybe there is some hope to do that, but obviously there's all of these structures at the moment are infinite, at least countably infinite, and so it's a bit more, possibly a bit tricky.
Okay. Too early to say, perhaps.
Maybe too early to say, yeah.
Folks, we still have a couple of minutes before the next scheduled talk. Any comments on this game semantics work? just while we're waiting, can I just ask the Popple folks, could you call the next speaker to the stage? Oh, here we are. Great. You're getting a big round of applause. Spontaneous, Hugo.
Oh, wow.
So well done.
Thanks. Thanks, Andy.
Thanks so much. Great stuff.